Something has just passed through our solar system. It is not from our world, nor from the belt between Mars and Jupiter, or the distant Kuiper belt beyond Neptune. This is from another star, July 1st, 2025. The Atlas telescope in Rio Hurtado, Chile, captured a point moving through the constellation Sagittarius. Speed, 221,000 kilometers per hour. Direction, straight into the inner part of the solar system. In a few hours, astronomers confirm the hyperbolic trajectory. This object does not orbit our sun. He passes by us only once. Its name is Tresi Atlas, the third interstellar visitor we have recorded. The two previous ones, Oumuamua in 2017 and Borisov in 2019, only slightly opened the veil. But this other one, it is enormous. On October 3, 2025, a spacecraft orbiting Mars got the closest view yet of an object from another star system. What they saw changes everything we knew about interstellar objects. The first image of the opening shows a blurred spot. Brightness, 18, weak signal. Most amateur telescopes would not be able to capture it, but professional studies are meant for this. The Atlas scanned since June 5th, capturing images unnoticed until the object was marked. Why? It passed right before the dense star fields of the galactic center, like a needle moving among other needles. Samdon, an amateur astronomer, tracks the first observations through archived data from June 5th to 29th. 34 days of images were stored on servers unnoticed while Tresi Atlas approached at a speed of 61 kilometers per second. At the Palomar Observatory in the Center for Transcendental Studies, even earlier photographs dated June 14th were found. This is the earliest confirmed observation. At that moment, Tresi Atlas was 4.5 astronomical units from the Sun, 3.5 from Earth, already active, glowing, and releasing gas into the vacuum. Within 48 hours of the official discovery, 3 observatories confirmed the presence of a coma. A deep random survey in Chile, the Lowell Telescope in Arizona, and the Canada-France-Hawaii Telescope on Mauna Kea all showed the same thing. A small halo, 3 seconds of arc, resembling a tail, not an asteroid, but a comet. David Jewett and Jane Liu confirmed on July 2nd at the Nordic Optical Telescope that the object is clearly active and appears blurry. The Minor Planet Center announced about Tresi Atlas on the same day. 122 observations from 31 observatories. The object is designated as 3 and is the third confirmed interstellar object. Additionally, C2025N1 Atlas is a periodic comet. It will never return. If you value documented interstellar exploration and advanced astronomical observations, subscribe. It's the best way to support our work. Also, let us know which city you are listening from. This script is based on research and facts, using data from the ExoMars mission published on October 7th, 2025, Hubble Space Telescope observations presented on August 7th, 2025, and results from the James Webb Telescope's NEARPEC campaign released on August 25th, 2025. It can be confirmed that these are peer-reviewed sources obtained directly from the instruments that recorded the data. Now let's get back to the essence. The question of size arose immediately. Initial brightness calculations indicated a diameter of 10 to 20 kilometers. Too large. Too large. This would mean it is heavier at once than 2 Borisovs. Huge interstellar objects are not detected until thousands of smaller ones are found. The math doesn't add up, but the brightness was real. Something was glowing. The Hubble Space Telescope pointed its mirror telescope at 3 atlases on July 21st, 2025. The distance was 446 million kilometers from Earth, 3.8 astronomical units from the Sun. The observation followed the hyperbolic trajectory of the comet. Stars crossed the frame in the background. The image showed a droplet of dust in the shape of a tear. Before there was a tail, there was only a compact glow 4,000 kilometers in diameter, modestly stretching towards the Sun. The core itself was invisible, too small even for Hubble's resolution. However, the limits became stricter. The upper limit was 5.6 kilometers in diameter. The lower limit is 440 meters. The most likely size is less than 1 kilometer, similar to Borisov. But here is the problem. The light did not come only from a small core. The brightness implied something much larger. The Cosmic Observation Device. SEX observed 3 in Atlas in the near-infrared range from August 8th to 12th. 3.0 micrometers, 4.26 micrometers, 4.7 micrometers. Water emission lines. Carbon dioxide, carbon monoxide, and water were not detected. Carbon monoxide was not found. Carbon dioxide was dazzling. A symmetrical cloud extended for 348,000 kilometers. This is 2.3 times the distance from Earth to the Moon. The mass loss rate was 70 kilograms per second of carbon dioxide. The upper limit for water was 4.5 kilograms per second. The brightness of SPHX at a wavelength of 1 micrometer suggested a nuclear diameter of 46 kilometers, if it were solid. If 99% of the brightness comes from icy fragments in the coma, the core shrinks to 5 kilometers. Yet, that is enormous. Still, it is 1,000 times the mass of 2 Borisovs. Avalope from Harvard calculated the consequences. For a diameter of 46 kilometers with an albedo of 4%, typical for Kuiper belt objects, the mass is 33 billion tons, 33 trillion kilograms. This is the mass of a small mountain range compressed into a comet. This creates an anomaly. Considering the limited amount of mountain materials in interstellar space, we were supposed to discover 100,000 objects the size of Muamma before finding 3 interstellar objects. But up to that point, we had only recorded 2 previous objects. On August 6, 2025, the Hubble telescope observed the object Ceton Tom Armand at a distance of 3.3 astronomical units from the Sun using the near-spec instrument, a near-infrared spectrograph with a resolution from 0.6 to 5.3 micrometers. Spectral images returned with results. The coma was dominated by carbon dioxide. Degassing intensified towards the Sun. Water vapor was present, but in small amounts. Carbon monoxide and other substances like carbonyl sulfide were also detected. Water ice substance with visible absorption characteristics was discovered. Dust was scattered everywhere. The ratio of carbon dioxide to water was 7.6 plus or minus 3/10, one of the highest levels ever observed in comets. 4.5 sigmas above trend for long-period comets and Jupiter family comets. Only one anomalous object in the solar system has similar proportions. Comet CU 2016 R2. What does this mean? 2 possibilities. Firstly, the object Ceton Tom Armand contains ice that has been influenced by higher levels of radiation than comets in our solar system, due to cosmic rays bombarding its surface for billions of years in interstellar space. Or, secondly, it formed close to the line of carbon dioxide freezing in its parent protoplanetary disk. This line defines the boundary where carbon dioxide condenses in the forming solar system, which is different from the freezing line in our system. This is another star, another chemistry. Matthew Hopkins, an astronomer from Oxford, defended his dissertation a week before the discovery of the object Ceton Tom Armand. His work, the Otauti model, predicted the properties of interstellar objects based on galactic populations. On July 1st, the day of the opening, he woke up to messages about a discovery, full of exclamations. His model predicted that objects from the thick disk of the Milky Way should be old, ranging from 7.6 to 14 billion years with a confidence level of 68%. The age of our solar system is 4.6 billion years. This means that the object Ceton Tom Armand may be older than all known objects. Chris Lintott, co-author and host of the BBC Sky at Night program, claimed that the likelihood of this comet being older than the solar system is 2/3. It has been wandering through interstellar space since then. Its trajectory tells a story. Hyperbolic speed decomposed into galactic coordinates. Component U1 is 51 kilometers per second, moving away from the galactic center. Component U2 corresponds to the rotation of the galaxy. Component U3 is positive, moving upwards through the galactic plane at 18.5 kilometers per second. This speed B is high. Most nearby stars do not move vertically this fast. 3 atlases move along a sloped orbit around the Milky Way, belonging to either a thin or thick disk population. The thick disk consists of older stars with low metal content and an ancient formation process. An independent analysis conducted by Astor Taylor and Dari Seligman in July 2025 estimated the age of objects to be between 3 and 11 billion years. This is confirmed by a broad consensus. These objects are ancient. A study conducted by Yizhang Wu in September 2025 showed that 3 Cine Atlas could pass within 1 parsec, which is 3.5 light years, from 25 known stars over the last 10 million years. These close encounters led to gravitational jolts, each slightly altering their trajectory and increasing speed due to gravitational waves. Tracking them back to their parent star is impossible. Too many interactions and too much time. They wander for too long. The comet continued its journey. On July 21st, observations were made with the Hubble telescope. On August 6th, with the James Webb telescope. From August 8 to 12, observations were made with SPHEREX. On August 21st, a large telescope in Chile detected cyanide and nickel in the comet's coma. Practically cyanide, specifically hydrogen cyanide. Its production rate, measured by James Clerk Maxwell's telescope, was approximately 1.5 plus or minus 0.5 multiplied by 10 to the 25th power molecules per second. On September 14th, production rose to 4.5 plus or minus 1.9 multiplied by 10 to the 25th molecules per second, which amounts to 2 kilograms of cyanide per second. The coma of September 15th had a diameter of 180,000 kilometers, asymmetrically elongated towards the side opposite the Sun. The visible dusty tail measured 50 angular seconds, approximately equal to 100,000 kilometers. The explicit value was 14.2. The nearest approach to Mars began on October 3rd, 2025. It was the closest distance to the red planet, 30 million kilometers, 18,600,000 miles. This would be the closest approach for any spacecraft. The ExoMars orbital spacecraft from the European Space Agency and Mars Express, which have been orbiting Mars since 2016 and 2003 respectively, have adjusted their instruments to observe the interstellar visitor. It was a pivotal moment, the chance to see the comet closer than any spacecraft ever had. The ExoMars orbital spacecraft, equipped with a color stereo imaging system, was designed to photograph the surface of Mars from a distance of several hundred to several thousand kilometers. However, it was not designed for faint and distant objects. Nick Thomas, the lead researcher, noted that this was a very difficult observation for the instrument, as the comet was 10,000 to 100,000 times fainter than normal targets. 5-minute exposures were used, layered on top of each other to capture signals. The angular resolution of the camera was 11.36 microradians, equivalent to 2.34 angular seconds per pixel at a distance of 30,000 kilometers, which is equivalent to 340 kilometers per pixel. The expected core diameter ranged from a minimum of 5 kilometers based on mass calculations to a maximum of 46 kilometers based on SPX brightness data. Even the largest assumption turns out to be less than 1 pixel. The images were obtained on October 7th, an animation published by the European Space Agency. A small blurred white dot moves down toward the center of the frame. Stars in the background stretch as Cassis tracks the comet. This blurred dot is the coma, a cloud of gas and dust several thousand kilometers wide. The core of the coma is indistinguishable at such a distance. It is like trying to see a mobile phone on the moon from Earth. Impossible, yet the coma is clearly visible. Brightness quickly diminishes with distance from the core. The total length could not be measured, as the faint outer regions disappear into image noise. Mars Express also attempted to conduct observations using a high-resolution stereo camera. The exposure time was half a second. This is the maximum limit for Mars Express. Too short. The comet did not appear in these images. Scientists will combine several frames from Mars Express to determine if their combination will reveal a visible weak signal component. The Mars Express Omega and SpyChem spectrometers, as well as ExoMars Go Nomad, attempted to take measurements. Whether the coma was bright enough for spectral characterization remains in question. Analysis continues. Colin Wilson, a researcher on the Mars Express and ExoMars projects at the European Space Agency, stated that while our orbiters on Mars continue to make impressive contributions to Mars science, it is always particularly exciting to see how they respond to surprises, as in this case. I eagerly await what the data will show after further analysis. The image of Cassis displays a bright glow, approximately 680 kilometers wide, which is about twice the diameter of the bright stars in the same frame. The sources are point-like. The comet's glow is diffuse. Avelo analyzed the surface brightness profile of Cassis from a distance of 30 million kilometers. The main mirror of Cassis, with a diameter of 13.5 centimeters, has an area 300 times smaller than that of the Hubble telescope's mirror. The detected glow at a distance of up to 680 kilometers matches the surface brightness profile of Hubble, intensified by increased sunlight near Mars, compared to where the Try-Me Astro Atlas was during Hubble's observations. This indicates that there was no significant increase in desaturation during the 3 months between observations. Steady-state activity. The stream of carbon dioxide from Sparix, with a radius of 348,000 kilometers, extends far beyond what Cassis could record. This stream with a spherically symmetrical shape is limited by the pressure of the solar wind. Hubble's blur showed a slight expansion towards the Sun, with a length-to-width ratio of about 10 over thousands of kilometers. A side view of Cassis, almost perpendicular to the solar axis of the Tri-Premium Atlas, confirms this geometry. The brightest area around the core is all that the Cassis device managed to capture. The outer shell, glowing below, is completely lost on Hubble. NASA's orbital Mars probe also observed Comet Triatalis. The high-res camera with a half-meter focal length was able to capture images with a resolution at a distance of 30 million kilometers, which amounted to 30 kilometers per pixel. This is better than at Cassis, but still not enough for direct core resolution. The data has not been published yet. NASA's closure in October 2025 delayed the publication. Colin Wilson from ESA mentioned that NASA's data looks quite good. Results are still awaited. NASA's rovers, Curiosity and Perseverance, on the surface of Mars, were attempting to observe the Martian night sky from ground level. It is not yet confirmed if they captured a comet. NASA has also not published these results. What do observations from Mars reveal about the true nature of 3 Atlas? The constant glow and structure of the coma over 3 months of observations, from Hala in July to Cassis in October, demonstrate stable degassing. No major emissions or fragmentation events were recorded. 2 Eorosoft objects fragmented. Comets often break apart when heated close to the Sun. 3 Atlas remain stable. This indicates a solid core or unusual composition that withstands thermal stress. The predominance of carbon dioxide is a key point. Ordinary comets are rich in water, ice, hydrogen, oxygen. The 3 Atlas hardly evaporate water vapor. Carbon dioxide activates activity at a distance of 3.32 astronomical units from the Sun. When Webb was observing him, the temperature was too low for effective sublimation of water. The freezing point of water in the solar system is about 2.5 astronomical units away. 3 Atlas was beyond this boundary, but carbon dioxide sublimates at lower temperatures, activating earlier. A high ratio of carbon dioxide to water, equal to 7.61, indicates that the environment of the comet's formation was rich in carbon dioxide, possibly due to high radiation exposure in its origin system or formation near the carbon dioxide frost line. The age of the comet, potentially reaching 7 billion years or more, supports the radiation hypothesis. If the 3 Atlas wandered through interstellar space for 3 billion years longer than our solar system has existed, cosmic rays bombarded its surface, leading to radiation effects, changing the chemistry of ice, depleting water, and concentrating carbon dioxide. Research on Kuiper Belt objects shows similar effects on much shorter timescales. 3 billion years of exposure could lead to extreme changes. The detection of cyanide and nickel using the Very Large Telescope coincides with the concentrations of comets in the solar system. This is surprising. If Atlas is so chemically different in water compared to carbon dioxide, why are the trace elements similar? This indicates that the main components, such as refractory materials, metals, and organic compounds, are universal. Different star systems produce similar raw materials. The composition of ice varies depending on the distance from the star and the radiation environment, but the basic chemistry remains unchanged. The mystery of size persists. If the core truly has a diameter of 5 to 46 kilometers, this is a huge size for an interstellar object. The argument about the Avalobi anomaly is weighty. We should not see something so large before discovering thousands of smaller objects, unless the 3 Atlases are not a coincidence, unless its trajectory was influenced by something. The coincidence with the orbital plane of the solar system is 1 in 500 for a random event. The trajectory brings it deeper into the inner solar system, passing Mars at a distance of 0.19 astronomical units on October 3rd. The perihelion is at a distance of 36 astronomical units on the 20th or 29th of October. This is between the orbits of Earth and Mars. Some researchers, including, suggested that the three atlases might be artificial, an interstellar station or technology, but the spectroscopic data from WebXRAN shows a clear cometary composition. Ice of carbon dioxide, ice of water, carbonate of sulfur, cyanide, nickel, dust. These are natural materials. Degassing follows the physical laws of sublimation. The speed of the ejected material, 0.44 kilometers per second, coincides with the thermal release of ice being heated. There are no signs of movement, no visible geometric structures in the images, only a blurred comet. The calculation of the minimum mass based on non-gravitational acceleration gives 33 billion tons. If 150 kilograms are ejected per second at a speed of 0.44 kilometers per second, the rocket effect produces acceleration. Three atlases show less than 15 meters per day of non-gravitational acceleration, despite significant degassing. This requires a massive amount of mass to resist the pull, at least 33 quadrillion kilograms, for a core diameter of 5 to 46 kilometers. The density is within the range of known comets, porous ice and rock, nothing abnormal in density, only absolute scale. October 29, 2025. Perihelion, maximum approach to the Sun. 1 whole 36 astronomical units, 203 million kilometers. The comet disappears behind the Sun from Earth's perspective. Solar conjunction on October 21st, 8 days until perihelion. Impossible to observe from Earth for weeks. Orbital Mars probes provided the last close look before sunlight obscured everything. In early December, 3 atlases will reappear from the other side of the Sun, visible from Earth again, but further away, accelerating towards Jupiter. The JUICE spacecraft of the European Space Agency, exploring Jupiter and its icy moons, is heading towards Jupiter and will observe Triton and Atlas in November 2025. It is equipped with many instruments, including cameras, spectrometers, and particle sensors. Collaboration is planned with NASA's Europa Clipper mission. Both spacecraft will be equipped with ultraviolet spectrographs, one on each vehicle. JUICE will be positioned close to the Sun, using its main high-gain antenna as a thermal shield. The connection will be limited by a medium-direction antenna. Data transmission speeds at great distances from Earth will be low. The device will be on the opposite side of the Sun, and the observation data from JUICE will only arrive in February 2026. The Juno spacecraft, orbiting Jupiter, will observe Triton and Atlas as it passes close to Jupiter in March 2026, at a distance of 0.36 astronomical units or 54 million kilometers. However, Juno has little fuel and engine problems. Redirecting to Triton and Atlas poses risks to the main mission, so this is unlikely. The NASA spacecraft Pike flew 0.30 astronomical units, or 45 million kilometers from Triton and Atlas on September 4, 2025. Observations were not conducted as it was too risky for the mission. The same applies to the researcher of Jupiter's icy moons during its passage in November. The main mission takes priority. After Jupiter, Triton, and Atlas will forever leave the solar system. The hyperbolic trajectory will not close. Escape velocity has been reached. They came from the direction of Sagittarius, from the center of the galaxy, and will leave in another direction, deflected by the gravity of the Sun. Where are they heading? We will never know. Deep space, wandering among the stars, adrift for several billion more years. Perhaps they will pass close to another star. Perhaps this star has planets. Maybe observers there will see them too. Or perhaps they will move in the dark, remaining unnoticed forever. The legacy of observations of Mars lies not only in images but also in coordination. 2 spacecraft designed for planetary science were repurposed with minimal notice to observe an interstellar visitor. The Cassis camera, intended for Martian geology, captures something from another star. Spectrometers are trying to make measurements at the limit of their sensitivity. This is adaptive astronomy, using what we have, where possible, when the opportunity arises. There is no time to build a special mission. Triton and Atlas are moving too quickly, and while you design, finance, build, and launch the probe, the target is already slipping away. You use existing resources, improvise, capture what you can. Data from the gas orbital apparatus will be analyzed for years. Spectroscopy, if successful, can reveal the ratios of isotopes: carbon-13 to carbon-12, oxygen-18 to oxygen-16, deuterium to hydrogen. These ratios vary depending on where and when the object was formed. Our solar system retains the characteristics of the protoplanetary disk that existed about 4.5 billion years ago. Comet 3 and Atlas formed in a different place and time. Its isotopes must differ. If the Nomad spectrometer on ExoMars T has recorded a sufficient signal, these proportions can be extracted. This will give us insight into the chemistry of the planetary system of another star. Direct measurement, not conclusions from remote spectroscopy of exoplanet atmospheres. We receive a real sample that can be analyzed up close. Observations on October 3rd recorded the closest proximity of a man-made instrument to an active interstellar object. The comet Oumuamua was discovered as it was leaving the solar system, without a visible coma or tail. The comet Borisov was thoroughly studied during its passage in 2019, but it had never been so close to a spacecraft, only to ground-based telescopes. 3 and Atlas were recorded by Mars's orbital devices at a distance of 30 million kilometers during their closest approach, active with a formed coma. This is the data set. This is what we have to understand interstellar visitors. Currently, it is known that the 3I Atlas has a probable diameter of 5 to 46 kilometers and weighs at least 33 billion tons. It is rich in carbon dioxide and poor in water. The comet is old, possibly 7 to 14 billion years. It came from the thick disk of the Milky Way. For billions of years, it wandered, pushed by countless stars, accelerating due to gravitational assists. The object is stable, not fragmenting, and constantly emits gas. It contains cyanide, nickel, carbon monoxide, traces of water vapor, traces of carbon dioxide, and a lot of dust. Its coma stretches for thousands of kilometers, and the stream of carbon dioxide extends for hundreds of thousands of kilometers. The core is too small to be seen directly, even with the best cameras we have in orbit around Mars. But it exists. Solid, icy, rocky, ancient. We do not know exactly its dimensions, mass, or the composition of the inner core. Is the surface uniform or diverse? Is the high level of carbon dioxide natural or radiation-induced? How much water ice is hidden beneath the carbon dioxide-rich crust? Will the object crack as it approaches the sun? Will it cause explosions? Is its rotation stable or chaotic? Where did it form? Which star expelled it? When did this happen? How many close encounters has it had with other stars during its journey? Is it a typical representative of interstellar comets or an anomaly? Observations from Mars provided the closest look so far, but it still remains a blurry spot. Several thousand kilometers of the coma are reduced to pixels. The core remains invisible. We need better tools, closer approaches, or we will wait for the next one. The Vera Rubin Observatory, which is starting to operate now. Over the next decade, it is expected that 5 to 50 interstellar objects will be found. This is an optimistic forecast from the Atlas III project, which suggests that the upper limit of this range could exceed 50 objects. Each of them will be unique, representing a sample of different star systems and preserving information about planet formation in other parts of the galaxy. Interstellar comets are time capsules formed around stars billions of years ago, possibly stars that no longer exist. Some of them could explode like supernovae, others could be consumed by black holes, and some could be completely ejected from the galaxy. But the comets born from these stars still wander, preserving the chemical traces of those distant systems. The comet Triatlas may have originated from a star that died 2 billion years ago. We will never know, but the comet remembers, the isotopes remember, the chemistry of the ice remembers. New data appeared in mid-October. The trajectory analysis, based on 5 months of observations from May 15th to September 23rd, was conducted with the help of 227 observatories that gathered thousands of data points. The observed non-gravitational acceleration was less than 15 meters per second squared. This is very little. With a mass loss of 150 kilograms per second, the comet should accelerate more. The rocket effect, the thrust of the expelled gas. But this does not happen. The mass of the comet must be enormous to withstand this thrust. Either its core has a diameter of 46 kilometers, or it is significantly denser than ordinary comets, or we have underestimated the rate of mass loss. Data from the Mars Reconnaissance Orbiter, when published, may clarify the situation. Measuring brightness with high rise at a distance of 30 million kilometers, combined with the known solar flux at that distance, can separate the brightness of the nucleus from the brightness of the coma. This will refine the estimate of the comet's size. The brightness distribution of the coma in Cassie images, when fully analyzed, will provide a dust density profile that will limit its formation speed. the data from the Nomad, Omega, and SpyCam spectrometers, if the comet is bright enough, will provide the gas composition from 30 million kilometers away from Mars, which is 3.32 astronomical units from the Sun at that moment. This distance, when Webb observed the same distance, allows for a direct comparison. The composition has changed. The ratio of carbon dioxide to water has shifted. New volatile substances have appeared: sulfide compounds, ammonia, methanol. The Hubble is observing the 3 Atlas in November, conducting ultraviolet spectroscopy. The V lines reveal the composition of gas emissions and the ratio of sulfur to oxygen. The chemistry of sulfur tells us about the primordial nebula where the comet formed. High sulfur content indicates that the comet formed in a sulfur-rich area, possibly near a young star with a strong stellar wind. Low sulfur content suggests that formation occurred in a calmer environment. Oxygen isotopes, if measurable, will be compared with data from the solar system. Each measurement reduces the number of possible options. Observations will resume in December, after perihelion. Observations after perihelion show the comet after maximum heating. After a period of maximum activity, it may remain intact or break apart, with activity decreasing rapidly or slowly. The shape of the brightness curve after perihelion shows the distribution of volatile substances in the comet's nucleus. If volatile substances are concentrated in the outer layers, the activity decreases quickly. If they are distributed throughout the core, the activity fades slowly as the comet cools. By March 2026, the TRES-Atlas comet will be beyond Jupiter, moving towards the outer part of the solar system at a speed of 68 kilometers per second relative to the Sun. It will only be visible in the largest telescopes. Ground observatories will track it for as long as possible, months, perhaps even a year, until it disappears below the detection threshold. With a brightness of 20, then 25, and it will vanish, returning to interstellar space. Another point among the stars, but the data remains. Images, spectra, light curves, isotopic ratios, if we obtain them. The brief visit of a comet to our vicinity provided information that cannot be obtained in any other way. We cannot visit other star systems. Not yet, not for centuries, but from time to time, very rarely, pieces of other star systems visit us. Oumuamua taught us about the existence of interstellar objects moving at high speeds. 2 Ivory Soft showed that interstellar comets are similar to comets of the solar system. 3 and Atlas teach us about their vast diversity. Ancient, massive, rich in carbon dioxide, stable, fast, old. This diversity is the galaxy. Millions of comets, each unique, wander through the space between stars. Recent observations from Mars' orbit revealed a constant, elongated comet made of dust and gas, predominantly carbon dioxide, with no details of the core, too small and too distant. But brightness, stability, chemical composition, trajectory, all confirmed. This is a real comet from an actual star system that existed in the distant past of the galaxy. 7 billion years ago, when Tri-Atlas could have formed, the Milky Way looked different. The Sun did not yet exist. Our solar system forms only in 3 billion years. The Earth existed 3 billion years ago. Life will appear in 4 billion years, and yet somewhere in the thick disk of the galaxy, around an old metal-poor star, ice and rock combined, a comet was formed. The gravity of a giant planet or the close passage of a neighboring star ejected it into the outer orbits. Speeding into the darkness, this object has been moving for billions of years, passing one star after another, subjected to gravitational forces and accelerating under the influence of waves. On July 1, 2025, it entered our solar system. A telescope in Chile detected it. Observatories around the world confirmed its presence. Hubble took its photograph. Webb conducted an analysis, and SphereX mapped its carbon dioxide plume. Mars orbiters captured it at the moment of closest approach. 30 million kilometers, 18,600,000 miles. A blurred white dot in the Martian sky, the oldest and largest visitor we have ever observed. On October 3, 2025, we received the closest look at this interstellar traveler that any spacecraft has ever had. What was revealed continues to be studied, and what it means we are still trying to decipher. But one can say with certainty, we are not alone in creating comets. Other stars do this too, and sometimes, quite rarely, these comets come to us, bringing messages in ice, stories in isotopes, secrets in carbon dioxide proportions. 3 and Atlas rushed by. Mars orbiters observed, data collected, and now we know a little more about how planets form around distant stars, how comets move through the galaxy, how ancient ice can travel through the emptiness of space between stars, waiting to be discovered. Observations in November 2025 from JUICE, awaiting data return in February 2026, may show Atlas at its peak activity after perihelion. Hubble's V spectroscopy in December will check the sulfur to oxygen ratio. Observations of the Webb after perihelion will measure the cooling curve. Each data point adds its part to the overall picture. Each spectrum refines the model. Each measurement brings us closer to understanding not only Tri and Atlas, but all interstellar visitors. Next, and another, from 5 to 50 in the next decade. The Rubin Observatory will scan, Atlas will observe, the Zwacky Transient Facility will record. Sooner or later, another point will appear, moving strangely, too fast, hyperbolically. And the cycle will begin again. Discovery, confirmation, observation, analysis, learning. 3. And Atlas, a massive wanderer with a thickness of 7 billion years and a diameter ranging from 5 to 46 kilometers, at least 33 billion tons, rich in carbon dioxide, stable, fast, ancient. Observed by Mars orbiters on October 3rd at a distance of 30 million kilometers, the closest view so far turned out to be exactly what the old models predicted, and was completely different from our expectations. A comet from another time, another place, another star, passed by once and has now gone.